Hi, my name is Jason Pleadwar. I'm an account manager at IRIDIAN Spectral Technologies, product group manager for aerospace and specialty optics, and proud to be presenting on optical filters for space applications here at Photonics Plus. IRIDIAN is a Canadian company. I'll tell you a little bit about us. We're a manufacturer of custom optical filters and coatings based in Canada. Myself and about 160 of my colleagues all work out of that building. Normally, I'm working from home, but they're all working in the building now. And we've been around since 1998. We're located in Ottawa, Ontario, Canada. This is where we do all of our design, sales, and manufacturing. And we're ISO 9001 2015 certified and part of the Canadian Controlled Goods Program. As mentioned, fundamentally what we do is manufacture custom optical filters. And these filters work in a wavelength range that spans from the upper end of the ultraviolet, about 300 nanometers, out into the long wave infrared, normally about 10 microns, but we've recently extended that to about 15 microns. We have different types of filter performance in these wavelength ranges: single band or multi-band filters, edge filters, notch, multi-notch filters, gain flattening filters, as well as multi-zone filter arrays. And I'll talk a little bit about that as it relates to Earth observation applications. The size of the filters that we provide ranges from as small as 1 square millimeter or less for some of our fiber optic applications, up to as large as 150 millimeters or so for astronomy applications and solar rejection filters. All of our filters are manufactured in our custom-built platforms. We have in excess of 20. We've lost track now, honestly. Energetic sputtering is our dominant technology, but we have added evaporation into one of our coaters to address the long wave infrared. The coaters are controlled by custom design and control software, and we also have a clean room to provide in-house photolithographic patterning for some of our multi-zone filter arrays. So the topic of the talk is optical filters in space applications, and the two markets that I'll talk about that are addressed with these filters and photonics in space are Earth observation and Satcom. So in Earth observation, I'm talking about instruments flying in typically low Earth orbit that are imaging or doing remote sensing of Earth to provide specific spectral information to ground-based users from above. This can be used in disaster response, floods, fires, in ongoing environmental studies and environmental analysis, and in industries such as agriculture and forestry to manage best practices. Satellite communication is a very different application. This is not providing information from above in terms of imaging or sensing, but it's providing an optical communication network, but rather than terrestrially based, as the fiber optic network is, based on a mesh network of constellations of satellites communicating with each other via optical laser links in optical intersatellite links. These Satcom networks that are starting to be deployed will be important in supporting 5G and the Internet of Things and the demand for low latency, high throughput networks to provide internet access to remote and rural communities that aren't otherwise serviced, and to provide secure internet communications. So all of this has driven a photonics space race where historically the participation in space was driven largely by working with space agencies, some of whom are listed here. Space agencies are still involved now, but with the changing dynamics of putting satellites and instrumentation in a space where the cost per kilogram to launch equipment has gone down by literally several orders of magnitude, and the capability of those instruments has gone up similarly, has made it a very attractive area to commercial entities. In Earth observation, some of the companies that participate are listed here. There are companies involved in creating the instruments for these Earth observation systems, or actually in creating and putting up their own satellites and providing that data as a service to folks down on Earth. And as a filter provider, we're working with those folks to provide the optical filters using those instruments. In satellite communication, there are fewer participants because these are large constellation networks, but the large companies like Telesat, SpaceX, and Amazon, as examples, are putting up, in the case of Starlink, they're talking about thousands to tens of thousands of satellites to create this mesh network of satellites and communication from the skies. The companies listed below are, again, a subset of some of the companies that are involved in providing the instrumentation that are those optical engines that function within those satellites. So for Earth observation, we provide two types of filters: single band filters, where we're looking at a single particular line of interest, as we're doing on a project, the Meteosat next generation lightning imager for ESA. So we're looking at a single large filter that's looking at a single wavelength band of interest, or multi-zone filter arrays, where different zones are going to provide different spectral bands to different pixels, creating multispectral imaging for remote sensing. In satellite communication, the optical filters are providing the same function that you would see in a terrestrial system. Wavelength division multiplexing with the dichroic beam splitters and combiners, bandpass filters at the detector or sensor to make sure that only the signal of interest gets to the detector, solar rejection windows to only allow the signal light into the satellites, and I'll talk a bit about that, and polarization preserving filters for applications such as QKD. In Earth observation, the example of a multi-zone filter is shown here, and we have a couple of approaches here. We can take individual filters, coat them, cut them into bars, and then glue them together into a butcher block style array. Or we can photolithographically pattern different zones on a particular filter. And again, creating those multiple zones where different pixels are going to have different wavelength selectivity and be able to look at different science bands of interest. Important characteristics of these filters are to have high transmission in those signal bands, and steep edges and deep blocking of the other spectral bands, and essentially giving great signal to noise of those particular bands of interest for each of those rows of pixels. From the filter manufacturer point of view, the challenge is to provide that wavelength selectivity while reducing and minimizing stray light within the system, band-to-band differences, coplanarity in the butcher block arrays, for example, and minimizing pixel loss due to defects, surface defects, and the dead zone between the bands. And this can be optimized with trade-offs for specific custom performances. So we like to work with our customers and understand what matters most, and then develop solutions that really target those needs. The example in Satcom that I'm showing here is one of the solar rejection filters. So the curve shows an orange curve, which is showing a high transmission of the spectral band. In the inset, showing you might have multiple wavelengths within that band that the solar rejection filter is transmitting. Also, additionally, importantly, it's providing deep and broad blocking of the black body solar radiation. This provides two functions. It improves the signal to noise at the detector. This is only getting the light you want to the detector, but also reduces heating within the satellite, and that can be important as well. Again, the challenge for a filter manufacturer here is creating that high transmission, deep, broad blocking over a relatively large part that is also important to maintain great transmitted wavefront error. We can't be distorting the signal that's getting into the detector, otherwise the communication signal can break down. So high wavelength selectivity, really very uniform filters, and creating those low transmitted wavefront error filters, a lot of which is dominated by the coating, is really critical as a filter manufacturer. Iridian's got a proven space heritage. We've been doing these types of filters for a decade now, and we've tested many of the requirements to fly in orbit in space: radiation, thermal cycling, vibration, etc. We've provided tests on the filters ourselves, but our customers have tested and used these as well. And we have there are hundreds of Iridian filters right now flying in space, providing both Earth observation functionality and satellite communication. So that's all I really have time for today. It's a short talk, but I'd be happy to address any questions via the chat or at our booth via chat as well. Or you can contact me directly by email, and I'd be happy to talk about your needs or any questions or needs for optical filters for space applications, or equally for terrestrial applications. We certainly deal with a lot of those as well. Thank you very much. Hang out here for another minute or two to see if there's any questions, and then if not, I hope to see you at the booth. Or great opportunity, if people haven't done, is to join the networking rooms and try those out. They're a lot of fun. Thanks, Oliver and Ian. Great to see that the two of you joined.